Hello, welcome to Everything Distributed. Last time we talked about the fundamentals of hash function. Today we are going to talk about three applications, how to apply hash functions inside Bitcoin. And the content is from this great book. It's called Bitcoin and Cryptocurrency Technology. In short, I will call it BCT. I highly recommend you to purchase it. And if you don't have enough money, that's fine. The authors generously provide preprint on their website here. So last time we talked about three kind of properties of hash function, and then one of them is called collision resistance. Roughly speaking, is that we have a hash function h, and it should be computationally infeasible, or it's hard to find a pair of two different strings x1, x2, such that hx1 equal to hx2. For illustration, suppose we have two different strings, x1, x2, so they have different colors, and we are using the same hash function h here, but somehow they produce the same output with the same color, hx1 equal to hx2, then this h is not collision resistant. In order for hash function to be useful in Bitcoin and in other like cryptography or security application, we want it to be collision resistant. So this kind of cases should not happen. And one application is message digest. In many times, in lots of applications, we don't want to send the message itself. Like for example, input here, the blue ones, we don't want to send it. Instead, we send a hash of our message. So the digest will look like just some random numbers. And because of the collision resistance, the digest is as good as the message itself, because it's impossible to find these two pair of string. They have the same digest. And that's the importance of collision resistance. Later on, we will see more applications of this message digest. And the second application is called commitment. So in real world, how does commitment work? You can think of that as that we have envelope and we have some secret message. We just put the message inside the envelope and then seal it and send it to someone else. And that's the first step. I commit to the secret message. And one important thing is about this envelope, because the messenger that take the envelope should not know what's inside. The message should be kept secret. But when the receiver get this envelope, he or she has the ability to open up, unseal the envelope, and verify that, oh, okay, this message, secret message, is actually from me, Louis, and that's called a commitment. And during this time, the secret message should not be modified. Okay, so that's a commitment. To put it more formally, like there are two properties. The first one is that the message can be kept secret. No one can look into the envelope unless I open up. So it's like given the envelope, it's hard to find a secret message. And then binding is that unless I open once I seal the message, I should not be able to change the message inside the envelope. So that's that I commit to this message once I seal the envelope. Okay, two property, hiding and binding. And actually that one of the property is related to collision resistance we talked about beforehand. So take a moment to think about that, which property is related to collision resistance. And then the next nice property of hash function that it should provide is called hiding. Formally is that it is hard to find x, some message x, given that hr or x. So this is the or operator, where r is chosen from a probability distribution that has high mean entropy. Okay, so it's a combination of the two things. R is some random string, and then X, you can think of it as a strings that you want to have. Then high mean entropy, what that means is that you have a set of potentially very large set of values, and then no particular value, it's likely to occur too often. You can roughly think that it's a uniform distribution for all the messages or all the strings. And the application is commitment. So now let's look at that formally in the digital way. How do we achieve commitment? So the idea is that I'm going to commit a secret message, MSG, and then this R thing, which is a nonce, which is a number that can only be used once, so it's nonce. And then once I do this operation, I will get this com, where com is my commitment. And the analogy is that message and nonce is already inside this envelope, and what I get is this envelope, where this envelope is represented by com, which is a binary value, and then that is my commitment. So I'm going to tell everyone, hey, this is my commitment. And later on, when someone want to say, okay, I want to see your commitment, please unseal your envelope, and I can use this verify function. So I will tell you, hey, this com is my commitment, and then this was my original message, and then this was the nonce I used. Then the verify function will do this computation for you, and it will return true if and only if com equal to this, my commitment. So the analogy is that, okay, now I'm going to open it up, and then you can check the secret message inside. If it's matched with what I commit, then it's good. It returns true, otherwise it returns false. So now it's a good time to stop here to digest what's commitment and how do I use a hash function to realize this commitment scheme. And then so now we have defined this commitment function, and then the output com. So the hiding property is that given com, it's invisible or computationally hard to find the original message. And then binding is that it's invisible to find two pair, message nonce and message prom, nonce prom, such that message is not equal to message prom, but they produce the same commitment. Because if binding is violated, then that means that even though I seal the message inside the envelope, I can still change the message freely. Okay, so that's not good. Then in terms of hash function, actually it's very simple. You just put the nonce and all message and then hash it, and then that would be your commitment. So why does this simple scheme provide desirable properties? Because it has hiding property. It's directly from the hash function's hiding property, and then binding is actually just a rewarding of the collision resistance. Okay, so that's the second application, and then later on we will see that why it's useful inside Bitcoin. And then the final application, and then actually that's a starting point of the Bitcoin, is a search puzzle, and it's a fundamental element of a proof of work, POW in short. So now let's look again at the other hash function. It's called puzzle friendliness. And then I would say that this is the distinct feature of the particular hash function that's required for Bitcoin. For many other cases, this property is not necessary. So now the formal way of stating this is that for every possible n-bit output value y, then it's hard to find x, which is that your solution or your guess, such that hr or x equal to y. And the second part is more important because this computation should be able to should take some time. Okay, so should be really fast. I mean, in time significantly less than 2 to the power of n. So it means that it's a much less than exponential time contribution. And this R, you can think of it roughly as a non-thing. Is again chosen from distribution with high mean entropy. So what exactly is a search puzzle? And in search puzzle, the setup is roughly has 3 input. The first one is a hash function that satisfies the puzzle friendliness property. And then we have a value, which we just call it ID. Roughly, you can think of it as a puzzle ID. And then again, it's chosen from some distribution with high mean entropy. And then finally, we have a target set Y. So the solution is that you just iterate through all the X, such that if you put ID or X inside your hash function as your input, then you will get some value. And then that value should be in one of the element inside Y. So remember, Y is a set. It could be a value, but in general, it's a large amount of values. So 2 things to remember for this search puzzle is that the first one, what does it mean to ID to be chosen from high mean entropy? Is that there's no shortcut, and then the best strategy to solve this puzzle is by birthday attack. And the next one, the solution, is that Y is a set. Obviously, if Y is only a single value, then it's very hard to find X. Then for exercise is that when does this puzzle become trivial, meaning that any value of X could solve the problem. Any value of X is the solution. Okay. And then if you can solve this exercise, then you will understand how does Bitcoin adjust the mining difficulty. And then next lecture, we will talk about like how does Bitcoin use this type of a search puzzle to enable the mining process. Okay, so that's all for this lecture. We talk about 3 applications of hash function in the context of Bitcoin. So we have message digest, we have commitment, and we have search puzzle. So that's all. Thank you.